Because chapter 16, we mostly deal with alcohols, and chapter 23, we're dealing with phenols. And the phenols actually can be considered as aromatic alcohol. So we know alcohol has a LQ group connect with OH group. A phenol, basically you have a phenyl group connect to OH group. So that's why I decided to put the chapter 3 just right after chapter 16. So but a little different from alcohol. Alcohol is considered single functional group compound because there's only one OH group. So all the reaction focusing on the OH group. And the phenols, now it has a hydroxy group, okay, and also a benzene ring. So it's a compound with two functional groups. And these two functional groups, they talk to each other. So the phenols reactivity sometimes similar with alcohols, sometimes similar to aromatic compounds, because under these two are talk to each other. Okay, so the one thing is the OH group. One major interaction is OH group can donate electron to the ring. This we talked a bit in the chapter 13. So that makes the ring much basically increase electron density. So this long tail effect increase electron density on the ring, and that makes the ring, the substantially more reactive in electrophilic, the aromatic substitution reaction. Okay? That we're going to talk about later on. Okay? But first, what kind of nomenclatures? So phenols usually are named as the derivatives of phenol with a carbon bound to the OH at the 1 position. So this is a carbon 1, okay? There's a carbon 1. So the first one is called phenol. Second one called 3-methylphenol. And the third one is called 5-chloro-2-methylphenol. So we always name the ring carbons, okay, in the based on first point of difference to minimize the locant. So this one always carbon 1. Then to minimize locant, it has to go this way. Okay. So this one is carbon 2, carbon 3, carbon 5, carbon 3, carbon 4, carbon 5, and carbon 6. You don't want to go other way around. Okay. If you go other way around, the smallest locant would be the 3. If the other way around, 1, 2, 3, 4, 5, 6. Okay. The smallest, if go this way, the smallest locant would be 3. Okay. We want the set of smallest locant based on first point of difference. And then we list those names based on their alphabetic order. So we call 4 or 5-chloro-2-methylphenol. And if we have acyl groups, usually carbonyl-based groups, takes priority over OH. And forget about that for the naming part. I will not test it. But this one, yes, I will test. Okay. So the just regular phenol derivative will be tested. Okay. And if you have 2 hydroxy groups on the benzene ring, we call diphenols. And diphenols, also just we call it, depending on relative location of 2 hydroxy groups, we call 1,2 benzene diol, or 1,3 benzene diol, or 1,4 benzene diol. And then more importantly, we can look at structure and the bonding. So the phenol structure is planar. So if it's planar, immediately there's implication, of the hybridization state of those atoms. And we all know the aromatic ring is planar, so every carbon is sp2 hybridized. Okay? Because of this part also is planar, there's a implication here, the oxygen, okay, lone pair, okay, also will be participated into the ring. Okay? So one feature I want to emphasize the carbon-oxygen bond. Okay, here is only 136 picometer. Sizably. I'm not saying substantially. Sizably shorter than the carbon-oxygen bond in regular alcohol, and that is because of this carbon-oxygen bond has a sizable double bond character, as we're going to see later on. And also, this carbon is sp2 hybridized. So the sp2 hybridized carbon compared to sp3 hybridized carbon, forming a stronger single bond than this this carbon. Okay? And the other reason, as I said, this carbon-oxygen bond has some double bond character. Where the double bond character come from? Because of this oxygen lone pair, keep in mind, can be donated to the ring. And if the lone pair donated to ring, you can write this resonance form. And in this resonance form, the carbon-oxygen bond is a double bond. Okay? So we say the carbon-oxygen bond has a double bond character. It's not true double bond, obviously, because if you if you move this lone pair here to the double bond, then you have to move this carbon double bond to move away. Okay? Let's say we move to this one, then the negative charge on the carbon is also to the hydroxy group. And obviously, we can further move this lone pair to here, become double bond. Then this double bond, pi bond, can move here, become the lone pair. And then the lone pair can further move here, become the pi component. And the pi component can move here, become a lone pair. So what you can see is this, out of the totally 4 resonance forms, 3 of them has a CO double bond, okay? And out of these 3 forms, always a negative charge on the ring. So this shows that based on the resonance effect of oxygen lone pair, the electron density on the aromatic ring is increased. So that's why the ring here compared to just parent benzene is substantially more reactive in electrophilic aromatic substitution reaction. And the electrophile will be heavily preferred to attack O and P sides because that's the sides. Those sides you have a much higher electron density, from the lone pair. Okay? The OP sides, they are, the heavily preferred. And actually, we'll see P side is even more heavily preferred than O side because much smaller stereo hindrance. Okay? But if you look at those 4 forms, okay, this form still is of greatest importance, okay, because this form is aromatic, okay. Rest of the forms are not aromatic, and all the forms have equal number of bonds. All those 4 forms have equal number of chemical bonds, and this one has aromaticity, so this form still is of the greatest importance. Okay? But anyway, what you can see, because of those 3 forms all have a carbon-oxygen double bond, so if we to describe the true structure, you need the resonance hybrid of those 4 forms add together. So that's why we say the carbon-oxygen bond has some double bond character. That's why it's shorter. Okay? And that's also why you don't see carbon-oxygen bond cleavage in the reaction of phenols because this bond is stronger than typical carbon-oxygen bond. You don't really see the breaks. Okay? Physical properties is what you can expect it. The phenol, because it has OH group, can involve in hydrogen bond. So the boiling point is actually substantially higher than its hydrocarbon counterpart. Hydrocarbon counterpart is thorium, has similar molecular weight, but the phenol has a much higher boiling point, like 71 degrees Celsius higher. And also phenol is somewhat water soluble, okay? Because it has a hydrogen bonds, okay? It can form hydrogen bond with water. Now because the phenol has the OH group, so you can guess just like alcohol, phenol is somewhat acidic. But what's unique about the phenols is if you look at pKa of phenol and then compared to regular alcohol, phenol is about a million times more acidic. So why that's the case? Why phenols are so much more acidic? The mostly can be justified by looking at the stability of conjugated base. So in the alkoxide, the negative charge, this conjugate base of alcohol, the negative charge is localized on oxygen atom. But in case of in the conjugate base of phenol, phenoxide, the negative charge is delocalized. How? Look at the resonance form. Okay, so this is the major resonance form phenoxide, but the lone pair can be donated to the ring. And if it's donated to the ring, the negative charge could be on the carbon also to the oxygen atom or para to oxygen atom, just like in case of phenol. Only thing difference is the phenoxide is even more willing to donate the electrons to the aromatic ring compared to neutral phenol. Okay, neutral phenol, because after all, the phenoxide is oxygen negative charge, so it's more likely negative charge makes the electron even higher in potential energy, so they'll be even more likely to move away from negative charged oxygen. So but because of this, what you can see, this four resonance form shows that the negative charge is delocalized over four atoms instead of single atom in the alkoxide. So the phenoxide as a base is much better stabilized compared to alkoxide because of better electron delocalization. That means phenoxide, they are generally much weaker bases. If a base is better stabilized, they are weaker base. They are more happy as they are. They are less likely to accept the proton. So that makes phenoxide much less basic than alkoxide. So that's why when the phenoxide is less basic, their conjugate acid is more acidic. So that's the fundamental concept of conjugate at the base. If the conjugate base is less basic, its conjugate acid is more acidic. That explains why phenol about 1 million times more acidic than alcohol, but still less acidic than the carboxylic acid. Why? You see, if you want the negative charge to localize to the ring, right? You want those three forms. It makes an important contribution. But still, out of those four forms, this one is significantly more important than the rest because it's aromatic. Okay? But if you look at the carboxylate, the conjugate base of a carboxylic acid, the story is quite different. So if you look at the let's say using acidic conjugate base of acetic acid, as example, acetate. Okay, this one, as we know, we can draw the resonance form. The other resonance form. I strongly suggest you do a lot of practice of resonance form drawing because only doing can help you understand. Okay? So if you look at those two resonance forms, they are actually, you probably can see these two forms, they are of exactly the same importance. They're equally stable. So that means the negative charge is completely equally dispersed on the two oxygen atoms. Okay? So that's why that means this guy has a better electron delocalization. Okay? So that means carboxylate is even less basic than phenoxide, or that give you, that's why carboxylic acids, they are stronger acid than phenol. Now, because of the one major reason is phenoxide being more stable than alkoxide, that makes phenol more acidic than alcohol. If we put a substituent on the aromatic ring, which can further stabilize phenoxide, that will, makes the corresponding phenoxide even more stable, less basic. Therefore, the corresponding phenols will even be more acidic. So here, you look at the substitution effect on the aromatic ring and how it will impact the phenol acidity. What you can see is that if you have electron donating group like LQ group, okay, or the alkoxy group, you slightly, especially LQ group, you slightly enhance the acidity, but not much. But you have electron withdrawing group like halogen, it increase acidity because pKa becomes smaller, so acid becomes stronger. If you have very powerful electron withdrawing group like nitro group, we know it's kind of most powerful electron withdrawing group we have seen so far. It can depend on how many nitro group you have on the ring. You actually can, the strongly enhance acidity of the phenol. So this is kind of understandable because we know electron withdrawing group, it can have to pull electrons towards themselves. So obviously make the negative charge better delocalized. So it makes the phenoxide more stable. That's not a surprise. But the one thing I really want you to pay attention to is if you look at those three, nitrophenol derivatives, those three, okay, all of them have a single nitro group on phenol. Only difference is the position of nitro group on the phenol is different. And you can see there's a sizable difference in the acidity of corresponding nitrophenol. So let's look at it. Okay. So if one thing you can see the 2 nitrophenol and the 4 nitrophenol, those two compounds, the nitro group is either ortho or para to the OH group. They are more acidic than the 3 nitrophenol. The nitro group is a meta to the OH group. So why that's the case? Again, we can look at the electron delocalization in the phenoxide. So if we look at the electron distribution in the phenoxide, the 2 nitrophenol phenoxide ion, that's the conjugate base of the 2 nitrophenol, and in this 2 nitrophenoxide ion, there's one very unique resonance form. What you can see is here that if the oxygen lone pair, okay, donate to the ring, then push this pi electron, goes into the carbon nitrogen bond, you make a CN double bond, okay, and then push the oxygen in a pi bond between the N and the O to the oxygen, okay. So what we should see here is the negative charge can delocalize all the way into the nitro group. And as we know, nitro group is a very, very powerful electron withdrawing group. So you will be happy to accept the negative charge. Okay. So this form, okay, if the negative charge goes into the nitro group, it's a more comfortable, the arrangement. So it stabilize the molecule. So for the 4 nitrophenoxide, you can have a similar resonance form. Basic negative charge go all the way into the electron withdrawing nitro group. And if you do the same thing for the 3, nitrophenoxide, That's a conjugated base of 3-nitrophenol. Okay, let's say do it here. Okay, we try to move it around. We try to move it around. Okay, but under no circumstance you can move the electrons into the nitro group. Okay, so let's say we can get to here. So we can move to the really close to the nitro group, but you cannot move into the nitro group. Okay, so you can get to the negative charge here. Okay, and you certainly you can further move it to here. Okay, just you cannot get into the nitro group. See, you can place a negative charge, the on the two carbons, okay, next to the carbon carrying nitro group, but you cannot place negative charge on this carbon. Okay, you can't. Okay, so that's basically you when for the 3-nitropenoxide, the negative charge, you cannot write a resonance form, in which negative charge goes into nitro group. Okay, that's why the 3-nitropenoxide, okay, is more basic than these two guys, because this guy negative charge cannot go into the nitro group, and the nitro group, as we know, is a very electron hungry one. Okay? So that makes because of this guy is more basic than those two guys, so its conjugate acid 3-nitrophenol is less acidic than those two guys, the OP version. And if you have multiple nitro groups, okay, so what you can see is basically if I have two nitro groups, the corresponding phenol will be even more acidic, but it will be such effect will be stronger if both these two nitro groups they are OP to the OH group, and this compound also has two nitro groups, but because these two nitro groups both are meta to the hydroxy group, so acidity enhanced effect not as good as the 2,4-nitrophenol. You can see obvious difference. Okay, this guy is it's about the 3 orders of magnitude less acidic than this one. Now, if you have 3 nitro groups on the phenol, and all of them are also opera to the OH group, that makes the phenol extremely acidic. The pKa only about 0.4. This guy is the more acidic than majority of carboxylic acids. Okay, so it's actually more acidic than phosphoric acid. Phosphoric acid pK is about 2 to 3. Okay? This guy is more acidic than phosphoric acid. Okay? So that's why the common name is called whatever acid. Okay? Although it's not really a carboxylic acid, but it's more acidic than phosphoric acid. Source of phenols. Okay, so the one in the industry level is produced by oxidation of isopropylbenzene, and that reaction is a free radical reaction, because oxygen itself is a biradical, and if you take a hydrogen from this benzylic carbon, generate a fairly stable, the benzylic radical, and then react with water in acid can give you both phenol and acetone. both of those two compounds are industrially useful. And the preparation of phenol in laboratory scale is used for, make use of a reaction we're going to talk about in the very last chapter. So we don't need to worry about for the time being. Okay? So the nature of occurring phenols, many of them can be found in the flavor molecules. Here are some examples: vanillin, the eugenol and thymol. Those are flavor molecules. And also, there are many phenols that can be found, quite a few, anti, the oxidants, like the kind of, in green teas, you have a pretty high concentration of polyphenol, like the one we have here, multiple OH group on one ring. And each OH group can enhance the electron density on the ring. Multiple OH groups make the ring even more electron richer than single one. So those rings are good antioxidants. It can, they remove harmful radicals from a human, system. So that's one of the reasons those, the antioxidants are good for our health, like green teas, and also those often those deeply colored fruits, vegetables, they also often are rich in antioxidants, deeply colored. And another probably pretty famous phenol is THC, is the psychological active, the component in marijuana. It's also a phenol. And then reactions of phenols. Okay, so let's first talk about the focusing on the aromatic ring of the phenol. So that's a kind of reaction we learned in chapter 13, but now we are looking at in great detail on phenols alone. And phenols, okay, they are, the nucleophilic at carbons because of we have pi electrons on the ring. Pi electrons are nucleophilic. Especially in phenols, the pi electron density is enhanced by the oxygen lone pair can be donated to ring. So the carbon is nucleophilic. But the complication of phenol is that in addition, though, the two carbon being nucleophilic, the oxygen can also, be nucleophilic. So basically, we need to, careful with the reaction conditions in terms of, in terms of which, the nucleophilic atom will be really doing the job